Hello, and this time we're looking at differentiation, but from first principles. So, back in the day, before differentiation was a thing, Newton and Leibniz, depending on who you believe, invented it first, whether you believe the controversy of Newton seeing Leibniz's notes and hiding them and claiming it as his own. I don't know, let's not get into that historical debate. They were looking at how do you find the gradient of a curve. And so here's a curve, it's a bit wobbly, apologies for that. And you probably know that if we drew a very wobbly, let's get that a bit straighter, no, still wobbly. If we draw a tangent to that curve, then we can find the gradient at this point here by doing the gradient of this tangent, so the change in the y value over the change in the x value. And what they said was, okay, well, we can't do that because for this instantaneous point on a curve, you know, there is no change in x and y at that tiny little point, and we don't want to draw a tangent in, we want to do it from the curve itself. So, okay, instead what we're going to do is we're going to start with our curve. Let's zoom in on our curve. So here's a bit of the curve here. And let's say, okay, we want the gradient at this point. So we'll say, well, let's take a little point up the curve. So if this is xy, then this is the point x plus a tiny bit of x. So delta x, little delta, means a little change in x. And y plus a little change in y is the point further up the curve. And we're really zoomed in here, so the distance between here is really, really small. So the gradient between these 2 points should be very similar to the gradient at this point, except my curve isn't very good at all and should sort of come down here really. So it looks very different. This is almost flat, almost going negative, but anyway, we'll accept my poor diagram skills. The gradient at this tangent, at this point here, should be pretty close to the gradient of this line that intersects the curve. And hopefully we know that the gradient formula is the second y value take the first. So y plus delta y, put it in a bracket, take y over x plus delta x minus x. Okay, so if you didn't know, that's the formula y2 minus y1 over x2 minus x1. That's the formula we're using for the equation of a straight line. Okay, well, what we can do is we can say, all right, we've got this curve, and we're trying to find out what the gradient of this line is. The problem is we've got x's and y's. Let's express the y's in terms of x. Now, for that, we need to know what this original curve was. So let's assume for a moment that this is the curve y equals x squared. And you have to do this from now, you have to do this separately for each equation you want to do it for. So for y equals x squared, well, let's rewrite all of the y's here in terms of x. So this one's okay because if we put x in here, we just get x squared. So that coordinate there is x and x squared. And here, well, of course, we're going to substitute the whole of this in. We're going to substitute x plus delta x in as x and then square it. So the y value, oh, I've lost my curve there. So something like this. Okay, badly drawn, never mind. So here it's going to be x plus delta x, bracket squared. Okay, so let's rewrite this thing, but with those all in terms of x. So we've got the change in the y values, so this is x plus delta x squared minus the original x squared over x plus delta x minus the original x. And we can expand this bracket, so let's get rid of this and expand that. That's x squared, x times delta x and delta x times x, so plus 2x delta x, and then plus delta x squared. And now we can do some deleting, so let's change colors. X squared take x squared, x take x, that all goes. So let's write it out. M equals 2x, that's supposed to be an m, crikey. That's making it worse. Let's start again. There we go. 2x delta x, that's what we've got there, plus delta x squared, that's all cancelled, over, well, it's all gone except for over delta x. And actually, we've got a delta x in all the terms, so we can cancel this delta x with 1 here and 1 from there. So let's rewrite that. Let's move that over. And we've got a gradient of m equals 2x plus delta x. Wonderful. Except what we said was that this gradient here, although it's pretty good, the gradient of this matches this, I've redrawn it, matches this tangent pretty well, but it's not perfect. So let's bring this point here further in. Let's bring it down to here or to here or to here or even closer. And the closer we get, the smaller we make that, the closer it is to this. So as we make this tiny extra bit of x and therefore the extra bit on the y, as we make this tiny bit of x go smaller and smaller, it tends to 0. So as we make that pretty much 0, bring it to infinitesimally small, then looking at this, well, gradient, that's not going to change, that's what we want. 2x, well, that's still 2x, and this tiny bit of x is becoming smaller and smaller and smaller until it's essentially 0. So it essentially disappears. And we end up with the gradient instantaneously at this point as 2x. And in order to write that, we said earlier that the gradient is the change in y over the change in x. That's supposed to be a triangle for capital delta. And we then sort of looked at, rather than big changes of x and y, we said what's the little change in y over the little change in x. And because now we've taken that delta x down to 0, well, we haven't really taken it to 0, we've taken it to infinitely small. So we then say that, okay, we're saying this gradient is dy by dx. So I don't think these should be 0, these should be equals, these should be arrows, really, shouldn't they? So a big change over a big change becomes a little change over a little change, becomes an infinitesimally small change over an infinitesimally small change. I think I still said that wrong. So we can say here dy by dx, meaning that the instantaneous, the infinitely small change in values here that gives us the gradient, the small change in y over the small change in x, infinitely small, is 2x, and that's our gradient. Now we can do exactly the same thing no matter what this is. So let's look at something slightly more complicated. Let's look at 4x cubed minus x squared. Okay, and it works in exactly the same way. So I'm going to get rid of the diagram because I think I need more algebraing space here. Okay, so the first equation, get rid of all this, apologies, taking a while, there we go. So let's go back to blue so we can annotate in red in a moment. So the first coordinate is going to be x and 4x cubed minus x squared. That's the first coordinate, the x value and the y value, but in terms of x. And the second coordinate is going to be x plus a tiny bit of x, and therefore we substitute this into this thing. So it's going to be 4 bracket x plus delta x cubed minus x plus delta x squared. Okay, I can't quite fit the bracket in there. So those are our two equations, two coordinates, sorry. And the gradient is going to be the difference in the y values over the difference in the x. So it is 4 bracket x plus delta x cubed minus bracket x plus delta x squared minus 4x cubed minus x, plus, because we're taking away a minus, so plus x squared, all over x plus delta x minus x. So we can just get rid of these x's straight away. Right, so it's cancelling down this thing that's going to be tricky. So let's just put equals for now. And we need to expand all of this, really. There might be an easy way to do it, but let's just expand it all and then cancel it all down. So if we expand this cubed, we're going to get x cubed times 4, so we're going to get 4x cubed. We're going to get x squared delta x. Delta x. There's 3 ways we can achieve an x squared delta x, and there's a coefficient of 4 in front, so it's 12x squared delta x. If you're not sure how I'm expanding this, then you need to write it out as 3 brackets and try all the permutations and then put a 4 in everything, or look at how you do it with binomial expansion. I'll just assume you know how to do that. If not, then you can let me know and I'll do a separate video. Right, where are we up to? So we've done that squared, so then we have 3 lots of x times delta x squared times 4 is another 12x delta x squared, and then we have plus 4 delta x cubed minus x squared minus 2 delta x, x delta x, times them together, and minus delta x squared minus 4x cubed plus x squared, all over delta x. Right, red pen time. Let's do some crossing out. 4x cubed, I'm sure I had a 4x cubed here, minus 4x cubed, minus 4x cubed, 4x cubed, gone. We've got an a plus x squared here. Why have I got that? Yes, because we were taking away that minus, so that's a plus, and we've got minus x squared there, so we can cancel those. And then we can do a cancel with delta x's. So cancel that delta x, cancel that delta x. One of those, so it becomes squared. There's 1 on there, and cancel one of those. Right, let's get rid of all of this. And we'll go back to the top of the page and we'll see what we've got left from all of that. So we'll go back to blue and we'll say that this equals, obviously looping back. Right, so we've got 12x squared there plus 12x delta x plus 4 delta x squared minus 2x minus delta x. Okay. Now, what I shouldn't have done is I shouldn't have deleted what our original equation is, but I'm pretty sure that it was 4x cubed. This was y equals 4x cubed minus x squared. I'm pretty sure that's what it was, but obviously you can turn the video back and correct me if I'm wrong. Pretty sure that's what it is. Right, so now what we say is this is what the gradient is for that line, but because we're going to make it infinitely small, let's go to the infinitely small change in y over x. That means that these small changes in x become infinitely small. Well, there's no small change in x here, so it's just 12x squared. There is 1 in this, so as that goes to 0, whatever that is times 0 is 0, so that disappears. Something times practically 0 squared is practically 0. Minus 2x, well, there's nothing wrong with that. Let's have a minus 2x there, thank you. And minus delta x, that's not an 8, that's a delta. So minus a small change in x there, well, that's going to tend to 0, so that's going to go. So we get our gradient as 12x squared minus 2x. And if we were to do this equation by the method that we know for differentiation, times the front by the power, divide by the power by, times front by the power, reduce the power by 1, we're going to get 12, 3 times 4, x squared minus 2 times x to the power of 1, which we don't need to put the power of 1, which is exactly what we've got there. Assuming that that was what I started with. I might have misremembered that, but I'm pretty sure. In which case, they've both got the same method. So hopefully you can see how it works, that what we're trying to achieve is basically just writing out the 2 coordinates that we had, on that line that intersects, x and x plus delta x, and then, x and the equation, yes, the substituted y, what y equals, and x plus delta x and the equation with x plus delta x substituted in, and then it's just a case of expanding it all and cancelling it all and getting to that point where you can cancel these delta x's and see what's left, that doesn't have a delta x in, getting rid of those, any term with a delta x kind of goes when you take it to the infinitely small, and then you have your differentiated expression. Of course, it's much easier to do it just by the rule of times the front by the power reduced to the power by 1, but if you're looking to understand why, or if you are, unlikely, but if you are asked to prove a first principles differential, then that's how you do it. If you have any questions, you can pop them in the comments, but I think we'll leave it there, and I'll say ta-ra for now.